Hello student, I am Dr. S. L. Munde, Assistant Professor Department of Mathematics, Sri RLT College of Science, Akola. Dear student, in this lecture we will see some recurrence formulae for JP of x. Then we will see some problems on that recurrence formulae of a JP of x. Okay. So first we will see the first recurrence formula, and that recurrence formula is defined as or stated as x j dash p equal to p jp minus x jp plus 1. Dash mean derivative with respect to x. Okay. Now we will see the proof of this. Okay. One know that jp equal to summation n equal to 0 to infinity minus 1 to the power n 1 upon n factorial gamma of p plus n plus 1 x by 2 to the power p plus 2n. Okay. Now take the derivative with respect to x on both sides. So derivative of this jp is, that is j dash p, jp dash equal to, so this term is constant term, so this can be written as it is. Okay. So derivative of this term is, that is x by 2 to the power p plus 2n minus 1, and derivative of this bracket, that is 1 by 2, so this is the 1 by 2. Okay. Now we will multiply on both sides by x, so this can be written as x j dash p equal to, so this summation term is add as it is, so here multiply x, so x by 2 term as it is, p plus 2n as it is, x by 2 to the power p plus 2n minus 1 as it is. Okay. So what is next step? So here x by 2, here x by 2 power p plus 2n minus 1. So this will get cancelled. Power 1 and this minus 1 will get cancelled. So only remaining is here x by 2 to the power p plus 2n, and this all the terms as it is. Okay. Now what is the next step? Now we will multiply this bracket. Now we will multiply this bracket p plus 2n separately. So we will get in first term summation n equal to 0 to infinity minus 1 to the power n. So this plus p divided by this denominator as it is, x by 2 p plus 2n as it is, plus summation. Okay, so summation, this term is as it is, only 2n is multiplied. Okay, that means separating this term. Okay, taking separate the p plus 2n term. So what is the next step? So here p is a constant, so take outside of the summation. So this can be written as summation n equal to 0 to infinity minus 1 to the power n divided by denominator is as it is. So x by 2 term is as it is. So again here x, we will take x is a common term outside of the integral summation. So this can be written as it is. So x by 2, so take x is common. So p plus 2n minus 1. We can write in this way. Okay. So which is equal to p, and this is nothing but jp by using the formula of jp of x. So this is nothing but the jp of x. So this is the formula of jp of x plus this x as it is, summation. So this term as it is, summation, this term as it is, minus 1 to the power n. Okay. So this term is as it is. Now dear student, here if we observe that in second summation the first term for n equal to 0 vanishes. If we put n equal to 0, the second term is vanishing. Okay, because n minus 1 factorial. Because n minus 1 factorial. Okay, that is infinity. Hence we start summing from n equal to 1. So we will take n equal to 1. Okay, so we will change this limit. So left hand side x j dash p equal to p jp plus x equal to, change the limit, x n equal to 1 to infinity minus 1 to the power n as it is, this term as it is. Okay. Now for n equal to s plus 1, now for n equal to s plus 1, then for n equal to 1, limit will be n equal to 1 and s equal to 0, n equal to infinity, s equal to infinity. Hence the above term will becomes, okay, so this term will becomes, so this can be written in the form of s 0 to infinity. So x j dash p equal to p jp plus x term as it is summation s equal to 0 to infinity, and minus 1 to the power n means that is s plus 1. Okay, so we will get n minus 1 means that is s factorial. So this can be written as gamma of p plus s plus 2 and x by 2 p plus 2s plus 1. Okay, so in this way we can write term. Okay, so what is the next step? So here p jp is as it is minus. So take minus one term of this one term outside of the summation. Minus x summation s equal to 0 to infinity minus 1 to the power s 1 s is as it is divided by s factorial gamma of p plus s plus 2 x by 2 p plus 1 plus 2s as it is. Okay, so this step is as it is. Okay, and we know that this is nothing but, so this is nothing but the term of jp of p plus 1. Okay, so this is the jp plus 1. Okay, so hence we can say that left hand side equal to right hand side, that is x j dash p equal to p jp minus x j p plus 1. Hence the result is proved. Okay, recurrence formula number is proved. Okay, now we will show that second recurrence formula. What is the second recurrence formula? X j dash p equal to minus p jp plus x j p minus 1. Okay, so similarly we can prove this formula. Okay, we know that jp equal to, okay, so this is the formula of jp. So differentiate with respect to x in similar way. So taking differentiation with respect to x, we will get this step. Okay, then again we will multiply x on both sides in similar manner, previous example as it is. Okay, so then we will take x by 2. So here x1 x by 2 power 1 and this one will get cancelled. Okay, so only remaining term will be as it is. Okay, then what is the next step? Then we will separate the term. Okay, then we will separate the term. Okay, so what is the here? X j dash p equal to summation n equal to 0 to infinity minus 1 to the power p plus 2n upon n factorial gamma p plus n plus 1 x by 2 p plus 2n as it is. Okay, so okay, now what is here? Now we will write 2p plus 2n, 2p plus 2n. Here we will take the adjustment p plus 2n, we can write in this way. Okay, only term change here. Okay, then we will separate the term, Okay, so minus p, that is this is the first term, minus p summation n equal to 0 to infinity and so on, plus second term will be 2p plus n. So this is the second term. Okay, only we take here adjustment. Okay, and this is nothing but that is jp, so minus p jp plus summation, so this term is as it is. Okay, so if you observe, okay, so this term can be written as x by 2 p plus 2n minus 1 into what is x by 2 x p plus 2n minus 1. Okay, we can write in this way. So what is the next step? Okay, here x we have taken outside, x here we have taken outside of the bracket, x by 2. Okay, so minus p jp plus summation this term, and this is nothing but j p minus 1. Okay, so hence the second recurrence formula here is proved. Now we will see some examples on a recurrence formula number 1 and recurrence formula number 1. So this is the first formula and this is the second formula. Okay, so what is the first example? Prove that jp of x equal to 0 has no repeated roots except at x equal to 0. Okay, so to prove this, example number 1, we will use the recurrence formula number 1 and recurrence formula number 2. Okay. So here we have to note that if A is a repeated root of Jp of x, okay, then Jp of A equal to J dash P of A equal to 0. Okay. Okay. So what is the solution? So to prove this theorem, or to prove this result of this example number 1, we will apply the contradiction method. Okay. So assume that A is not equal to 0 is a repeated root of Jp of x equal to 0. So therefore which implies Jp of A equal to Jp dash of A equal to 0. Let us reconsider equation number A1. Okay. Now we will use recurrence formula number 1 and recurrence formula number 2. So by using recurrence formula number 1, so this is the recurrence formula number 1 and this is the recurrence formula number 2. Okay. So from this we can write Jp plus 1 of A equal to 0. Put x equal to A. We will get Jp plus 1 of A equal to 0 and Jp minus 1 of A equal to 0. So by using this result we can write equal to 0. Okay. Hence the two different power series have the same sum function, which is a contradiction to our assumption, that is Jp of x equal to 0 cannot have the repeated roots except at x equal to 0. Hence we can show that Jp of x equal to 0 has a no repeated root except at x equal to 0. Okay. So this is the proof of the example number 1. Now we will see the second example. Prove that x square j double dash p plus x square minus p square plus p jp equal to x j p plus 1. Okay. So to prove this theorem or to prove this example number 2, we will use the recurrence formula number 1. The recurrence formula number 1 is given as A1. Okay. So we will differentiate with respect to x. So differentiate with respect to x, here we will apply the product rule. First function into derivative of second function, that is j double dash p, plus second function derivative of first function, that is j dash p into 1, equal to derivative of this term, that is p is constant j dash p, minus again here we will apply the product rule, first function derivative of second function plus second function derivative of first function. Okay. So minus multiply we can, okay. Now we will multiply x on both sides. So this can be written as x square j double dash p plus x. So here we will jp we will transfer to this side. Then we will take jp dash is common, that is 1 minus p j dash p equal to, and right hand side will be only, that is minus x, that is minus x square j dash p plus 1, and this minus x j p plus 1. Okay. Now we will substitute the values of x j p dash from A1 and x j dash p plus 1 from A2. Okay. So therefore x square j double dash p plus 1 minus p j dash p equal to, that is p jp minus x jp plus 1 from equation number A1 equal to minus x jp dash, that is minus p plus 1 jp plus 1 plus x jp minus x jp plus 1 as it is. Okay. So after simplifying, after taking the calculation 1 or 2 step, we will get the required answer, that is x square j double dash p plus x square minus p square plus p jp equal to x jp plus 1. Okay. So this is the example number 2. Okay. Now we will see the example number 3. Example number 3, what is, show that j0 square plus 2 j1 square plus j2 square plus j3 square plus and so on equal to 1. And also we have to show that or deduce that mod of j0 of x less than equal to 1 and mod jp of x equal to less than equal to 2 to the power minus 1 by 2, where p greater than equal to 1. Okay. Now we will see the solution. We have already discussed the example number 2. So putting the values of p equal to 0, 1, 2 in previous example. We will get dd of dx j0 square plus j1 square equal to 2 by x 0 minus j1 square. Okay, so dd of dx j1 square plus j2 square equal to 2 by x j1 square minus 2 j2 square. Okay, so which equal to dd of dx j2 square plus j3 square 2 by x 2 j2 square minus 2 j3 square. Okay, so in this way we can write these steps. So adding these three equations, we will get dd of dx j0 square plus 2 j1 square plus 2 j2 square plus j3 square plus and so on 2 by x into 0, that is 0. Okay, so integrating on both sides with respect to x, we get j0 square x plus 2 equal into x plus this is integration constant c. Okay, so taking the integration of this term, derivative will get cancelled. So taking x equal to 0, so we will get j0 of 0 equal to 1, j1 of 0 and j2 of 0 and so on equal to same, equal to 1. So we get c equal to 1. So putting c equal to 1 in this equation, we will get the required result, that is j0 square x plus 2 j1 square of x plus j2 square of x plus j3 square of x plus and so on equal to 1. Now we will find out the result number 2. So from equation number a1, j0 square of x equal to 1 minus, we can write in this way, 1 minus, so transferring this term to right hand side, 1 minus 2 j1 square of x plus j2 square of x plus j3 square of x plus and so on, we can write. Okay, so if you observe here, j0 square j1 square are the negative terms, non-negative terms. Okay, so therefore j0 square of x less than equal to 1 we can write, and the modulus of this term will be, that is j0 of x less than equal to 1. Okay, so again from equation number a1, from this equation number a1, we can rewriting j0 square of x equal to 1. Okay, so this equal to 1 up to n term, we can write up to n term, that is equal to 1. Okay, so j square n of x equal to, so transferring this term to right hand side, we will get minus term, all the term as it is. Okay, so if you observe in bracket, each term will be the non-negative term, so therefore we can write 2 times j square n of x less than equal to 1. So that is j square n of x less than equal to 2 to the power minus 1, transferring this 2 to right hand side. So therefore modulus of mod j n of x equal to less than equal to 2 to the power minus 1 by 2 for all n greater than equal to 1. Okay, so this is the second result of this problem number 3rd. Okay, so in this way we have seen today recurrence formula number 1 for 1 and 2 and 3 examples on a recurrence formula number 1 and 2 for a JP of x. Okay, now I will give you 2 examples on this topic. Okay, so this is the first example you have to solve that, and this is the second example. Okay, so you have to solve these 2 examples as a homework.